Swayam Prabha. Digital India. Educated India.
We have proved the reciprocity of resistive two-port networks, but only for 3-terminal two-ports. Now, we will see how it can be very simply extended to 4-terminal resistive two-ports. Okay. So, let us say we have a 4-terminal two-port like this, and it consists only of resistors. Okay. Now, what is it that we want to prove? We can prove this in terms of any of the 4 parameters. Let us say we think of proving Z12 equals Z21 for this network. Okay. Then, what does it really mean? So, let us say I connect I1 to port 1 and nothing to port 2. I leave port 2 open circuited. Clearly, what comes out at port 2 between these 2 points is Z21 times I1. This is from the definition of Z parameters. Okay. And similarly, let us say I connect I2 to port 2 and leave port 1 open circuited. The voltage that I get here would be Z12 times I2. Okay. Now, what I have to prove is, let me call this V2, and just to distinguish between these two, let me call this I2 hat. Then the voltage here would be Z12 times I2 hat, and I will denote that voltage by V1 hat. Okay. So, the hat refers to the second case, without the hat it is the first case. So, essentially V2 by I1 would be Z21, and I have to prove that that is the same as Z12, which is V1 hat by I2 hat. Okay. So, essentially the open circuit transmission parameters from one side to the other side, that is what I have to prove to be equal for both sides, from port 1 to port 2 and port 2 to port 1. So, this is how I will go about proving the reciprocity for 4-terminal two ports, and I will use the results I already know from 3-terminal two ports. Okay. What I will do is, since I already have the proof for 3-terminal two ports, that is 2 ports in which there is a terminal common to the 2 ports, I will also try to define this in the same way. I will define this 1 prime as the reference node. Okay. So, then this is port 1, as we already know. Okay. My actual second port is between 2 and 2 prime, but of course, nothing prevents me from defining another port which is between, let me call this as A, between node A and the reference node. Okay. So, let us say I call this port A, and this 2 prime I will label as B, and I will call this port B. The actual second port I am interested in is between 2 and 2 prime. Okay. So, that is what I will get to prove, but now essentially I have defined 3 ports with a common terminal. Okay. This 1 prime is defined to be the common terminal, and this between this terminal 1 and the reference node, that is one of the ports, terminal 2 and the reference node, that is another port, just to distinguish it from the other two ports that we already have. I will call that port A, and between terminal 2 prime or B and the reference node, I have the third port, which is port B. Okay. So, now if I take any two of these, so let us say port 1 and port A, or port 1 and port B. So, each of these is a 3 terminal 2 port. Remember, the network is resistive. I can define the ports anywhere I want. The ports given to me are between 2 and 2 prime, and I will eventually prove reciprocity for that port. But I am now defining two other ports with the same common terminal as port 1. So, I can take any two of these ports and use my earlier result for 3 terminal 2 ports. Okay. So, what does my earlier result for 3 terminal 2 ports say? If I take this case, that is, take port 1 and port A as the 2 port network, I know that Z1A is ZA1. Okay. And similarly, if I take port 1 and port B as my 2 ports, I will have Z1B equals ZB1. Okay. Fine. So, now let me try out the two cases. In the first case, I will apply I1 to port 1 and leave port 2 open circuited, and let me define this as the reference node. If I leave port 2 open circuited, then port A is also open circuited, because I do not have anything between this and the reference node. Remember, this is terminal A and my reference node is over there, and this is terminal B and the reference node. Since I open circuit to 2 prime, I also have an open circuit at port A as well as at port B. Okay. So, what is the voltage that appears at port A? Clearly, I can think of port 1 as one of the ports, port A as the other port. So, if I inject I1 into port 1, what comes out here is ZA1 times I1. Okay. ZA1 is the parameter from port 1 to port A, and similarly here at port B I will have ZB1 times I1. Okay. So, I calculate these two voltages by first considering 1 and A as one of the two ports, and then 1 and B as one of the two ports. Since I do not connect anything to these two ports, that is okay, right. If you really want to, I could draw two separate pictures for this and that, but when I apply I1, I will get some voltage here and some other voltage there, which I can express in terms of the two port parameters between port 1 and port A and port 1 and port B. Okay. Now, what is my actual second port voltage? V2. This is V2, and clearly you see that by using KVL around this loop, we will have V2 to be ZA1 minus ZB1 times I1. Okay. So, I have applied a current here and found out the voltage on port 2. Now, let me take the other case, where I open circuit port 1 and I want to measure V1 hat when I2 hat is applied over there. Okay. So, again it is the same network, of course, the same resistive network that I have been taking all along. Now, this is also an opportunity for me to use one of the earlier theorems that we discussed. What I will do is the following. Okay. My calculations were with this point as the reference node, and I had defined two other ports, port A and port B, with this node being the reference node. This was port A, it was between this terminal and reference node, and this was port B, which is between this terminal and the reference node. So, what I will do is the following. I have copied this over, then I will split the current source I2 hat as two identical current sources in series. So, I can do this because the series combination of two identical current sources is exactly the same. We have seen this in the earlier theorem that we discussed as splitting of the current source, and we also saw that we could connect this node to any point in the circuit, and I will choose to connect it to the reference node. Okay. Now, why do I do this? By doing this, I see that this upper current source is basically exciting port A, and this lower current source is exciting port B. Okay. I already know the results between port A and port 1 and port B and port 1. I know that reciprocity holds. So, that is why I do it like this. Okay. So, now since I have two sources here, I will use superposition. So, I will split this into two cases where I have only the upper current source active over there and only the lower current source active over there. Okay. Now, what is the voltage I get at port 1? So, now port A is fed with I2 hat. So, at port 1 I will get Z1A times I2 hat, okay, with only this current source being active. Now, if you look at the lower picture, port B is excited with minus I2 hat because of the direction of the current source. Okay. So, here port A is excited with I2 hat, and here port B is excited with minus I2 hat, because the current flowing into port B is minus I2 hat. Okay. So, the voltage here is minus Z1B times I2 hat. Okay. Now, in the original case, I have both of these sources being active. So, the actual voltage V 1 hat would be the sum of this voltage and that voltage. Okay. So, the voltage here would be Z1A times I2 hat minus Z1B times I2 hat, or Z1A minus Z1B times I2 hat. Okay. So, pretty simple. I split the current source, took one current source at a time, got the outputs, and I have this as my output at port 1 when port 2 is excited. Now, I also know that port 1 and port A form a reciprocal 2 port, port 1 and port B form a reciprocal 2 port. So, this is nothing but the same as ZA1 minus ZB1 times I2 hat. Okay. So, the voltage that is developed here V 1 hat is the same as ZA1 minus ZB1 times I2 hat. I think you are already able to see the reciprocity here, but just for completeness, the parameter Z21 will be V2 by I1 with port 2 open circuited, that is V2 by I1 in this circuit, which turns out to be ZA1 minus ZB1. Okay. And the parameter Z12 would be V1 hat by I2 hat in this circuit, which is also ZA1 minus ZB1. So, that is equal to Z21. Okay. So, by a simple extension, we can prove reciprocity for a general 4 terminal resistive 2 port. Okay. So, this is proved, basically we have proved that Z12 equals Z21, and in doing that we used reciprocity in 3 terminal resistive 2 ports, and we also used the earlier theorem on splitting the current source and superposition. Okay. Because we were using reciprocity in 3 terminal 2 ports, we had to define some other ports with a single common node as the reference node. Okay. And we were able to do that quite easily. Hope that is clear.